Log on, tune in, find out. Another good idea from Cambridge.
Today's morning session, our first speaker is Yukinobu Toda of Tokyo University. His title is Stable Pairs on Local K3 Surfaces.
Okay, so I'd like to thank the organizers to invite me to this conference. So I'd like to talk about some geometric application of verb crossing formula to the K3 geometry. So, let S be a K3 surface. So S is a smooth and projective K3 surface over complex number field. That is S is two-dimensional. Canonical line boundary is trivial, and H1 OS is equal to 0. And I'm interested in the total space of the canonical line boundaries. That is a trivial line boundary. That is X is a total space of the canonical line boundary. That is, of course, S product affine line. So this is an example of the non-compact Calabi seafold. So the goal of this talk is to relate two kinds of invariants on this on this non-compact Calabi seafold. That is, the goal is I'm going to relate two kinds of invariants on X. That is, one of them is the so-called stable pair invariance. That is introduced and studied by Pandhai and Thomas. And other invariant is counting semi-stable sieves. So this is a classical notion of semi-stability, that if you choose a polarization here, you can define the classical notion of semi-stable sieves on X. That is that as compact support. So that is, other invariant is shift counting invariant. This is counting usual classical semi-stable sieves. But I also include strictly semi-stable sieves. So its definition of the invariant is not trivial. So this is essentially introduced by Joyce when there is strictly semi-stable objects, strictly semi-stable sieves. Sorry. Oh, thank you. Yeah, these two kinds of invariants have different features. So, the left-hand side, stable pair invariants. This is geometrically to do with curve counting invariants. This is related to curve counting invariance. So there is a conjecture relating stable pair invariance to the so-called reduced gamma-fit invariance on this non-compact cavernous report. And also, the definition is easier in the left-hand side, so in some sense. So this is actually z valued. Okay, so the right-hand side. So this is counting much more classical object, but including if you want to include strict semi-stable sieves, then it's much more modern invariant. And also, I can show that in the right-hand side, I can show that there is a certain automorphic property. And but so unfortunately, this is not z valued, but this is q valued. Okay, so I'm going to recall these two notions now. So first, I recall the notion of stable pairs. So by definition, a stable pair is this is a pair of F and S. So I always assume that F has compact support, or equivalently F has support on the fibers of the second projection. So F is contained in the category of pi x. This is, by definition, this is coherent sieves that is supported on fibers of the second projection. So this is second projection. And the assumption is that F is one-dimensional, and it is pure. That means there is no subsieve that has zero-dimensional. And S is a map from OX to F. That is, this is surjective in dimension 1. So this means that if you take co-kernel of this map, then it is zero-dimensional if it's non-empty. Okay. Is there some? So this is roughly speaking a pair of curve on X and a divisor on that curve, roughly speaking. And I'm interested in the moduli space of such pairs. P and X beta. So this is a theoretically this is a pair of Fs, and F is second homology of F. The fundamental class of F is equal to beta, and the homomorphic Euler characteristic of this one is equal to n. So beta is an element of H2 xz. But from the definition of x, you can also identify this one in the element of H2sz. And n is an integer. It can be shown that this is a quasi projective variety. Yes, so this is a definition of stable pairs and its moduli space, and this kind of invariant defined from these moduli space is previously studied by Kawai and Yoshioka, and they completely computed its topological order characteristic in terms of modular forms. So the Kawai Yoshioka's work is they compute topological order characteristic of this invariant. But under the assumption that the curve class beta is irreducible curve class, when beta is irreducible. So this irreducibility assumption is that means that this is, by definition, beta is not written as a sum of beta 1 plus beta 2 for some other effective one cycle classes. Beta I is effective one cycle class. So this is a very strong assumption, and if you assume this, then you can understand the geometry of this modular space explicitly and study its topological order characteristic. And I'm going to state the result in more detail. Yes.
On the support, are you asking that it's just reduced structure? Isn't the fiber scheme theoretic support?
No. That is supported on fiber, so not scheme theoretically supported. So there may be what? Yes. Yes. So the result of Kawai Yoshioka is that, so this is the result of 2000, and the first one is that, so the important assumption is that assume that beta is irreducible. Then in this case, first they show that this modular space is smooth. This is smooth, and it only depends on homomorphic chunk character n and beta square, but this is up to deformation equivalence. Actually, in this case, by the reducibility assumption, the one-dimensional C field is actually scheme theoretically supported on fibers, and the study is reduced to the pure K3 geometry. And then I write P and H to be the topological area characteristic of this moduli space. If beta square is written as 2h minus 2. So this is a first statement, and the other statement is that if you form a generating function of this invariant, and H P and H Q H minus 1, then so this generating function can be written as in this way. So this is square root of square root z minus and delta z q by 1, and this is delta z k is the infinite product given in this way. So you can completely calculate the topological area characteristic when the curve class is irreducible. So one of the goal for the study of curve counting invariants on KC surface is there is a so-called Katzken buffer conjecture, and when curve class is that is primitive curve class, then it was proved by the work of Marwick, Van Hypen, Thomas, and they reduced the computation of the so-called reduced Gromov invariant to the invariant counting stable pairs, and when the curve class is irreducible, and then reduce the computation, reduce the result to the Kawai-Yoshioka result. So that is Marwick, Van Hypen, Thomas, so that is then, and they prove the so-called the reduced version of Gromov-Witten and Van Hypen-Thomas correspondence plus Kawai-Yoshioka result. Okay, so sorry, for primitive curve class. So primitive means that so this beta is not written as a multiple of some as an effective one cycle. This is then combining these two arguments, they prove the so-called Katzken buffer conjecture. For primitive curve classes. But all the argument works for the assumption that curve class is primitive or curve class is irreducible or somehow. And the goal of my talk is to extend Kawai-Yoshioka's result without this strong assumption. So the natural question is that by Kawai-Yoshioka's result, we know the topological order characteristic of stable pair modular space for stable pair invariants when the curve class is irreducible. So the question is, there's some nice formula for the order characteristic of modular spaces for stable pairs when data is not necessarily irreducible. The idea is to relate this invariant to other invariant, that is shift counting invariants, which I mentioned before. Okay, so far is the review of stable pair and stable pair invariants. So next I talk about some other invariant, that is shift counting invariant. So this is, roughly speaking, the order characteristic of modular space of semi-stable sieves. That is a classical G-scar semi-stable sieves on the local on this non-compact Caviar seafold. So let me introduce some notation. So by definition, X is a product of S and a fine line, and I have two projections. So S. So the first projection is denoted by small p, and the second projection is denoted by pi, and so I have the map functors. That is, first you can take push forward from sieve here to here. So the definition of this category is that sieve supported on the fibers of this one. So if you take push forward, then it gives a coherent sieve on S. So this one is very defined, and also you can take the so-called Mukai vector, that is taking Chan character and multiplied by the square root of dot S. So this gives a map from this category to the so-called Mukai lattice.
Yukinobu, could you
Yes.
move that border?
Okay. So H tilde that is 向かいlattice, that is this is H0 Hz plus H2 Hz plus H4 Hz. Like this, and you can define inner product. This is Mukai inner product. That's defined by R1, beta 1, N1, and R2, beta 2, N2. So this is defined by beta 1, beta 2 minus R1, N2 minus R2, N1. Also, there is a rate 2 Hottie structure on H tilde S tensor C. So this is H tilde 00 is H00 H tilde 11 is equal to H sorry, H20 is H0, H11 is 0 plus H11 plus H22, and H02 is equal to H02. So in this way, you can define weight Hottie structure with the inner product here. So okay, so using this notation, let omega be an amp divisor on S, and if you pull back omega by P, then you can define the notion of omega discrete semi-stable sieves on coherent sieves on X supported on the fibers of pi. That is omega r beta n. So this is by definition moduli stack of we pull back omega discrete semi-stable sieves by X, and with, sorry, I should write that. I denote this composition by small v. So this is denoting Mukai vector. So this Mukai vector is equal to R beta n. So if this Mukai vector is primitive, and omega is taken to be generic, then this is essentially usual classical moduli space of stable sieves on the KC surface S. But I also include strictly semi-stable object, because if this Mukai vector is not necessarily primitive, then there may exist a strictly semi-stable object here. So I need to take account of the contributions of such strictly semi-stable object, and I use moduli stack, not class moduli space. And the invariant time interest D is defined by taking its Euler characteristic, that is I denote by J R beta n, to be, roughly speaking, this is Euler characteristic of this modular stack. But this is not precise. So, as I said, if this Mukai vector is primitive and omega is taken to be generic, then this modular stack is essentially a usual modular space. So you can take Euler characteristic in a usual way. But if there is a strict semi-stable object, then this is just everything stack. And it's not trivial how to define its Euler characteristic. And to define this, the definition of this Euler characteristic, this one is essentially defined by choice. That is, roughly speaking, taking the so-called logarithm in this of this modular stack in the mochilik Hall algebra, like taking in the so-called Hall algebra. I will not recall its definition. But because I'm taking log, so this is not a z variant, but this is q variant invariant. So as I said, if this Mukai vector is primitive, then this is a classical counting invariant, and this is essentially studied by many people. Especially this is relative to the Euler characteristic of the Hilbert scheme of points on KC surface. So, but before this, maybe I should note that. First, the definition itself, in defining this invariant, you have to choose a polarization omega. But you can show that this invariant, J R beta n, does not depend on the choice of polarization omega. So this one does not depend on omega. So this is essentially a consequence of Wolff-Cauchy formula. That is, Euler pairing of this category is trivial, so there's no Wolff-Cauchy if you change polarization. So this is essentially proved by choice. And secondly, if with the element of the Mukai vector that is primitive, then this modular space is essentially deformation equivalent to the Hilbert scheme of points on KC surface S. So it is JV is equal to the Euler characteristic of Hilbert scheme of points on S. So here is a usual Hilbert scheme of points. So this was this equality was studied by many people, maybe Hoiberist, Ogrady, and Yoshioka. And also, the Euler characteristic of Hilbert scheme of points on KC surface is also explicitly studied.
the section of this moduli space. Do we lose the section from our stable pairs? This is just the moduli space of the abs.
Yes, there's no section. This is just semi-stable object on the fibers of the second projection. So there is no section. So there is no framing. Okay.
No, but do you need irreducible
No,
5-vector here?
no. Here.
No,
no?
this Hoibrexa Grady Yoshioka.
No. This Mukai vector is primitive. So if you don't assume, if beta is not irreducible, if you take R that is coprime to beta, then this V is primitive. So this result can be applied. Okay. Beta is not necessary. Beta is not necessarily irreducible here.
In this pi x, are you asking that it be supported on only one fiber or possibly on many fibers?
Yeah, possibly many fibers. So yes, thirdly, this Euler characteristic of Hilbert scheme of points on S is given by the modular form. So if you take a generating function of Euler characteristic of Hilbert scheme of points on S, then this is equal to the this is given this way. So this is the get formula. So by these two results, you know that we know JV if V is primitive. But if V is not primitive, then the definition itself is very difficult. I'm taking logarithms of whole algebra, so it's difficult to compute. But at least for the primitive V, then this is completely calculated. So, okay. Now I'm going to state my main result. So main theorem is the following. So if I denote by pt chi x, this chi means this is I'm taking just straightforward Euler characteristic. So if I take a generating function of Euler characteristic of stable pair invariance, but I don't assume that beta is irreducible here. So n beta and y beta and just n. Then this is written as pt chi x. Maybe I can. So I like here. So the result is this generating function is equal as p chi x is equal as the infinite product. This is exponential and plus r j r beta r plus n y beta beta n. Exponential and plus r j r beta r plus n y beta beta minus n. So this is a result. As I said, this is also a consequence of word crossing formula. So this formula completely reconstructs the Kawai-Yoshioka's result. That is, I mean, if beta is irreducible, then this Mukai vector is automatically primitive. So you can explicitly calculate JV in this case.
So this beta is an effective class.
Yes. So,
But that, the semi-group of effective classes depends on the K3 surface, right?
yes.
So this is not a deformation invariance.
Uh,
But for an individual surface.
yes, this one itself is not deformation invariant. So, but because if you move KC surface, then the curve class deforms the other side here. So let's assume that beta is irreducible. So if you assume that beta is irreducible, then the theorem implies that
Yeah. Well, isn't there a contradiction then? I mean, on the left you have something that is a deformation invariant.
yeah, but if you want to understand the curve counting invariance on KC surface, the usual definition of Donaldson-Thomas type invariance does not work. So you have to consider so-called reduced invariant, and that invariant is invariant under deformation of KC surface. That is invariant under the curve class is algebraic. Okay. So if you define usual Donaldson-Thomas invariant, then it's trivial because beta can be deformed to no algebraic way. So if beta is irreducible, then the theorem implies that and beta is reducible and n is bigger than or equal to 0, then this is equal to, so n plus r, they are beta r plus n, and equal to so if beta is irreducible, then if you expand this formula, then you always just take this part. But you don't have to take exponential. And if beta is irreducible, then these Mukai vectors are primitive, so you can compute it explicitly. So this is, of course, chi heap beta squared minus plus 1 s. And using get formula and using this equality, then some computation, you can reconstruct Kawai-Yoshioka's formula. So unfortunately, I cannot give a complete answer for the invariant of JV when V is not primitive, but there is a prediction.
In the summation, is that n or r?
Yes, it's not R, yes. This is a finite sum. And yes, so this computation works because I know the invariant of JV when V is primitive. But the problem is that what is the invariant of JV when V is not primitive? So the question is, what is JV when V is non-primitive? So there is a hint because in defining JV, I did not include I did not include the framing of the sieve. So because I don't take account of framing, this invariant have some nice symmetry. So one of them is let G be a Hodge symmetry of the Mukai lattice. So as I said, there is a weighted Hodge structure on this lattice. Then JV is equal to JGV. So this means that if you want to calculate this invariant for some specific V, then applying Hodge symmetry, then you can also compute some other invariant. So this is also proved by word crossing, but I conjecture much more stronger condition on this invariant JV. Actually, the conjecture is that this invariant can be written as a Euler characteristic of Hilbert scheme of points on S by multi-covering formula.
Yukinobu, are you saying that this J of V is deformation invariant?
No, at this moment I cannot show that. I hope.
Conjecturing it. You're conjecturing it that it's deformation invariant?
Yes, I'm going to give a conjecture that if I assume that conjecture, then it also implies the deformation invariance when the curve class is algebraic. Okay. So the conjecture is JV is equal to the sum of gamma V 1 carry V over K plus 1 is. So this is a conjecture. Of course, this conjecture does not contradict his theorem because by Hodge symmetry, then Hodge symmetry preserves this inner product. This is unfortunately I cannot prove this conjecture at this moment. I checked this equality in some specific examples. But if I assume this conjecture, then this formula looks much more nice. That is if I assume conjecture plus the formula of this one, then the generating sheets Pt chi x is written as product expansion if one s multiplied by I beta minus get minus n. Yes. So so because we know this value by Get's formula, so this gives a complete answer of the Euler characteristic of modular space of stable pairs when curved class may not be irreducible. Okay. So in the last 10 minutes, I briefly explain the outline of the proof. This is a very rough story. Sorry.
If this is deformation invariant, do you think this is also the answer with the Behrend function put back in?
Yes, yes, I think so, but I haven't yet checked it.
Sine? There must be a sine.
Yeah, maybe, maybe I don't think sine is not needed. I think maybe. Okay, so okay, outline. So I just explain what kind of category I'd like to Wolff crossing. So first, for some technical reason, I compactify X. So X bar is S product P1. And I think D to be also you have map from here to here. I consider triangular category generated by the pullback line boundary here to here, and also the category of coherent field that is coherent field on X bar that is supported on the fibers of this second projection. So this is a so this is a smallest triangulated category of the Birkhoff X bar that includes these objects. So studying this smaller category makes the argument easier. Okay, so this is step 1. And the second step is I want to find some good T structure in which I want to apply Wolff crossing. So I choose omega. This is amplitude divisor, and then I can construct some heart of T structure on that triangulated category. That is generated by also phi the peak P1 and also some other object that is T omega F omega F T omega T omega shifted by -1. So this means that smallest extension closed subcategory. So this is a category that is generated by. You can also consider slope semi-stable object in cos pi x, but and this one is generated by mu omega semi-stable sheaves. And with the slope is less than or equal to 0. So this one is also generated by mu omega semi-stable. And it's mu omega is positive. And also plus torsion, or 1 or 0-dimensional sheaves. So actually, I can show that this is a out of boundary T structure on this triangulated category. So this is so as a third step, I would like to find stability conditions, or more generally, the so-called weak stability conditions. So this is, I want to find stability conditions on A omega, and which have some nice properties. So that is sigma 1 and sigma 2. And if I denote this modular stack of semi-stable object in this abelian category, so if I denote m sigma I 1 minus r minus beta minus n, that is modular stack of sigma I semi-stable object that have Chern character is equal to 1 minus r minus beta and minus n. And the point is that I can find weak stability conditions on this abelian category, so that if I choose some specific one, then this modular space essentially coincides with the modular space of the stable pairs. That is sigma 1 minus r minus beta minus n. This is for every r. This should be isomorphic to the, essentially isomorphic to the modular space of the stable pairs. And for other stability condition, so this is more or less trivial. That is, if beta and n are 0, then this is empty. And this is equal to pi star op1 minus r if beta and n equals 0. So in this sense, if I consider modular counting invariance, counting sigma 2 semi-stable object, then it is essentially trivial because there is only one object here. So I can, by applying word crossing formula from sigma 2 to sigma 1, then I can get a
What is the difference between the two conditions?
Sorry.
In that bracket, there's two cases.
This is two different choice of stability conditions.
Additional beta is n.
This one? Sorry, what's your question? Sorry, I don't understand.
Oh, there's a typo. You wrote two things the same.
Oh, sorry. Yeah, sorry. Oh, sorry. This is. Okay, so I stop here. Thank you very much.
But why can't you prove this conjecture? What's the
I don't know. It's difficult.
In this theorem, you mean you have derived the autoequivalence,
Yes.
which induces G.
Yes. Yes.
More questions? Then let's thank the speaker.